So you find the slope of each one. We're writing point slope form. So once again, I chose to use this point, y minus 41, the slope, x minus 43. And now for part B, you need to get those in the calculator. And so just move the 37 over, make it a plus 37, and then type in the calculator. Do the same thing with the other equation, y1, y2, and then second calc 5 will give you the point of intersection. So once again, we got it into y1, y2, did second calc 5, and that got us the point of intersection. Second calc 5, enter, enter, enter. So 55, 25 is our point of intersection. And our window settings were up to 100 both ways, and that worked out well. So I want to go up to around 100. Now there's 15 marks. So what should I go by? In fact, tell me this. What is the minimum scale I could use that'll include, well actually, like this point here is at 98. So if I want to go to 100 at least, what's the minimum scale I could use? Yeah, and the answer is 7s. And there's more than one way you can figure out. One thing you could do is just try and, like 6 times 15, you try that, you find it's not enough, it only goes to 90. And 7 times 15 is in fact the smallest number that gets you to 100 at least. If you don't like 7s, you want to go by 8s, that wouldn't be bad. They get you to 120. 10s, it's a bit big, because then you get to 150 that way, and that's substantially bigger than what we need. So we're going to go by 7s, okay? So start scaling your axes. And what I want to do is at least get the y-intercepts accurate. So look it up and tell me what the y-intercepts are. If you just look in the table, they're the first thing you see. At least they were in mine. That's for my table set up. Messed up. Yeah. So something. I want 66 to be on your graph. It's like there's 63. The next number is 70. So it's somewhere in there. We're just going to estimate. 77, 84, almost there. 91, 98, which is, so the other y-intercept's just above that point. Now, we're just going to estimate the point of intersection. I'm just going to count over. That was, well, okay, if we're going by 7s, the 8th mark, 1, 2, 3, 4, 5, 6, 7, 8. The 8th mark will be 56, won't it? If you're going by 7s. So I need to plot this point of intersection. It'll be a little bit to the left of that mark, and in between 21 and 28 vertically. Something like that. Like it's 25 for the y values. That'll do. And frankly, just draw your lines now. And you'll have to draw them because you can't cheat like me. Use a straight edge if you have one. Otherwise, just do your best. And there, that'll do. All right. Let's move on. Part C is trying to find the speed. For that, you need to first try to figure out the distance that they traveled. And for that, we're going to use distance formula, which is really just Pythagorean theorem. And frankly, we already know the horizontal and vertical distance that they traveled. It was the 8 and 6 for this player. I'm going to ignore the negative signs, but he went like down 6 and over 8. But this is just a 3, 4, 5 triangle. What's the answer? Yeah, because this is 3 doubled, that's 4 doubled, so this is 5 doubled. Now that is 10 yards, which he traveled in 1 second, so his speed is 10 yards per second. When you do the defensive player, the funny thing is you get the same numbers. It was 6 and 8. So oddly enough, they're going the exact same speed, which I think is probably unlikely. But it could happen. All right, now we'll get this part. We'll do the offensive player first. Someone tell me the starting point. The offensive player. And after 1 second, where was he? And then if we keep tracking this, the x values were increasing by 8 every time, so increased by 8 again and again. The y values were decreasing by 6, to decrease by 6 again and again. Okay? Now you do the defensive player. You should have gotten these numbers, yes? By the way, the question below it, what's the answer to that? That's where the tackle happened, right? And that's what I would say is, you can just put that's where the guy got tackled, which means motion stopped, which means these don't actually exist, right? At the 3-second mark, they were both on the ground, presumably, or maybe getting up. They're certainly not moving the way they were. So on the graph, the reality is, if I go back to this graph, this part isn't reality. The model, if you extend the model that way, then fine, it would cross paths there, but they didn't cross paths. I mean, like they didn't keep going. So that's one thing you need to understand. We make these mathematical models, and they're just that. They don't last forever, in other words. Eventually, they don't match reality, because reality doesn't go on forever. So you can talk about like exponential growth. Well, things can grow exponentially for a time, but not forever. Anyway, all right, last part. I don't know why that's there. I'll do the offensive player first. His x value started at 39 and increased by 8 every time. And then his vertical started at 37 and decreased by 6 every time. And there you go. You have parametrics that not just model, it's not just good equations for that line, but it gets the speed right. Because watch this. If I wrote this, x equals 39 plus 4t, and y equals 37 minus 3t, I'd have the same slope, but I'd be traveling at a slower rate. Okay? And so that's not appropriate for this situation, although it would produce the same line. Write down the other ones for the defensive player now. Nathan, you just tell me, what's the horizontal? That's correct. Nathan, you take the vertical. So, there you go. We're done. Okay? Good. All right, look at number 2. And number 2 is what we did yesterday. You have the picture and all the information is in the words as well. The initial speed is 103. And let me say again, pay attention to the units. They need to match. So the height is 4 feet. So it's feet per second. That's speed. That's good. But they could change them up, not make them match. This is just time. To remind you, that's the variable. Now, write down the horizontal equation. They gave you the vertical here, but they don't have the horizontal. So write that down. And what I want you to do first is basically complete a table. Hold on. And I'll even give you the equation. So the initial speed was what again? So put 103 there. Cosine of 28. That's an 8. Squint and you'll see that it's so. And then write the vertical equation. I can do this. All right, and it was plus 4, is that right? So that's me. What I want you to do is put your calculator in parametric mode, type in these 2 parametric equations, and go to the table and get this filled out. And just list the, I just want a little table here. The 3 horizontal distances, 3 vertical distances, and move on. Now look up here. Before you do that, I want you to understand. Okay, listen carefully. The last 2, we need to calculate the maximum. We need to calculate the 0 of this function, okay? The problem is the calculator doesn't have that ability when you're in parametric mode. In fact, if you're in parametric mode and you do the second trace or second calc, you'll see there's, in fact, here, I'll show you real quick. If I do second trace, okay, hold on. I'm in rectangular mode. So go ahead and put your calculator in parametric mode right now because you're going to need it for this part. And so I'm saying if I'm in parametric and I do second trace, I get this. Nothing about calculating the maximum or minimum or zeros or point of intersection or anything. You just can't. So I'm saying for this part here, for part C and D, what you're going to do is take your vertical equation and type it in, but you're going to type it in as a y equals x equation. You're going to go into function mode, and you're going to take this equation and type it in, like I said. What you have to remember is you have an x there, but what does that x represent? The time, right? In other words, this isn't actually a graph of the trajectory where you have the height, the height is based on the horizontal distance that the ball has traveled. That's not what this means now. It just gives you the height based on time. But if you put that in the y equals x mode, it can calculate the maximum for you. But it'll tell you the maximum height and when it happened. So I'm saying, when you get to the assessment, you got to keep this in mind. You may be dealing with parametric equations, and that is a parametric equation, but you're actually going to take that and put it in function mode to be able to do the calculations you need to do. Listen, one more thing I need to stress. I guess my point is, you start looking at the table here, you can get an idea of what the maximum height is going to be. You can get an idea. But when I ask you to calculate the highest point, I expect you to do second calc max. If you're trying to find zeros, calculate it. If you're tracing, you're not going to get the right answer. Okay, the table also usually does not give you the right answer. It give you close, but I expect you to calculate. All right, get this done. Now, once again, to calculate either max or the zero on a function, once you get the equation into y1, and let me reiterate, what we typed in here is our vertical equation, but x really is the time. It's not the horizontal distance, it's the time. And so when we did the window settings, we made the x max like 5 because that was 5 seconds. Originally we had like 100 feet, but we changed to 5. At first we had a really bad graph. Now, to calculate the maximum, you do second calc 4. And then you need to get the idea that when you do this left bound, right bound, these questions to ask. Here, let me show you. Imagine you have a screen with multiple maxims. Then you need to define your left bound, right bound, so it will find the right one. You're telling which part of the screen to look on, basically. That's all you're doing. So here, and if you want to have a left bound, just make sure your cursor is to the left. So you can either cursor over to the left to the maximum, and then just press enter, or you can select it. So the right button just needs to be something definitely to the right. The right side of the screen is I set to be 5, so I can just type in 5. I get it down to the right bound. And for guess, just press enter. And then there you go. And that's what I wrote down. The maximum height was 40.535. It occurred at 1.51 seconds. To find the time, I did the same things. I did the zero function. I did second calc 2. And that's this point here I'm trying to find, where it hits x-axis. Left bound is already good. Right bound, I'll choose 5. It's right at that point again. And there you go. The zero is 3.1 seconds. And let me reiterate. If you try tracing, you're not going to get a good answer. I mean, if I trace up to that vertex, I'll get something close to 40.53, but you won't get the right answer. All right, now looking at number 3. First of all, everyone look up here? The circle, this is a really simple thing, because what you have is Ferris wheel. It's saying it's going to make the center of the circle at the origin, and the radius is that. So x squared plus y squared equals that radius squared. You're done, right? Now the parametrics. Look, this is a little bit tricky. You want to start at the lowest point, so draw this on your paper. Draw your circle. Put a star or something indication that we're starting at the bottom, and we're going counterclockwise. So draw your arrows going counterclockwise, all right? So here's your thought process. If you want to figure out your starting point, you want to focus on cosine. We want our y value to be at the minimum, start at the minimum, right? So make your y equals equation have cosine in it, but negative cosine. Don't forget, you need a coefficient of 67.5. But that way your y value starts at the minimum, because cosine starts at the maximum normally, but now in this case it starts at the minimum. And then we want to travel to the right initially. So I'm going to use sine. Sine starts at the minimum. Here, put 67.5 sine of t. Now, sine starts in the middle. Should I keep it like this to make it go counterclockwise, or should I make it a negative? Keep it like this because I want it to increase, and sine would start in the middle and increase, right? So that's how you want to do these. Here, we're going to get through this real quick. How much time to cover 90 minutes? It was half an hour for full rotation. So half a circle is 15 minutes, and 90 is half of that, so 7.5 minutes. Okay, because if you didn't notice in the problem, it said it took 30 minutes for a full rotation. Pretend that says minutes. Or maybe I'll just make it look good. What about the next question? Yeah, 12 degrees per minute. 360 degrees, it did that in 30 minutes. 360 divided by 30 is 12. Now, our parametric equations, look, I'll just give this to you. We're writing the same equations, except for now, put 12t in there for both of them. And think about that. So when t is 1, it's traveled, by the time t is 1, it's traveled through 12 degrees. By the time t is 30, it's doing sine of 360, isn't it? So that works. Now, we're going to do number 1 at the bottom real quick. Draw the picture. You want to start at the lowest point and go clockwise. And we'll just keep the 12t in there. If you want to start on the lowest point, once again, you put cosine in the vertical equation and make it negative. But we want the x value to start in the middle and decrease. So this means be a negative 67.5 sine. There you go. So your homework is twofold. One is just finish this. Number 4 we'll do in class on Monday, okay? Just finish this. That shouldn't take long. And finish up the bookwork from yesterday.